everyone. In this video, we're going to start talking about congruences. So before I define them, let me talk about some examples. Congruences are really useful. It's a really useful tool to talk about remainders of numbers, and it has lots of applications. People are actually used to congruences because we use clocks. Clocks are something that runs on a congruence modulo 12 usually, but here I've drawn a clock that is modulo 24 for a clock that would keep track of the hour of the day in the AM and the PM. So let me give you some example of what I'm talking about. So for example, suppose that it is now 2 p.m., which is the 14th hour of the day. And then we want to know what would be the time after 27 hours. Well, we actually only care about the time within the 24-hour clock. So I want to know, is it the 0th hour, 2nd hour, 6th hour, up to the 23rd hour? So what I'm going to do to calculate that would be I start with 2 p.m., so the 14th hour, and I'm going to add 27 hours. And that gives me that it will be 41 hours and the 41st hour. But again, I don't care about the 41st hour. I care about an hour between 0 and 24. So what we're going to do is reduce that modulo 24, or in other words, do a long division by 24, because when I do a long division by 24 or subtract multiples of 24, I subtract entire days, and then I'm going to see what time is it afterwards. So 41 is 24 times 1 plus 17. And again, what happened here was that I did long division. Long division by 24. And then what I get is that it will be after 27 hours, it will be a whole day will go by, and then it will be the 17th hour. So it will be somewhere here, which corresponds to that is 5 p.m. It will be the 17th hour or 5 p.m. Right? We can do this also more generally. Let's see what happens. So this is one question. Let me ask again. What's the time after, let's say, 320 hours? Then we're going to do exactly the same. I would start with 14, add 320 hours, and that gives me that is the 334th hour. And then I just care about the time within my clock. So I do long division. Okay, I'm going to call here long division. Long division. And when I do long division here, I've done it before. This is 13 times 24 plus 22. And the question is not asking me how many days have gone by. It's only what time of the day it is. So this is sort of like superfluous. So I don't care so much about this part of the equation. What I care is about these 22. So it's the 22nd hour. So it will be the 22 hours. And the 22 hours are right here. That is 10 p.m. And this is an illustration of a system where we don't care about anything other than the remainders when we divide by 24. Let me give you another example, which is more in the theme of the book, or in the theme of how I approach number theory, which is a Diophantine equation. So before, we have seen how to find solutions of polynomial equations. So rational and integer solutions of polynomial equations. And then we've also used things like the GCDs and the Zoo's identity to find points on lines. So equations that are of this form, we've done that. But what about now if we have a quadratic equation, something like a hyperbola? So, so the question is, are there any points on the hyperbola x squared minus 3y squared equals to 2 that have integer coefficients? So in other words, i.e., are there R and S integers? I'm going to call them N and M actually. Are there N and M integers such that N squared minus 3M squared equals to 2? Okay, so is that so? By the way, if you want to graph this hyperbola, so this hyperbola, let's see, how do we graph this? This hyperbola has the points square root of 2 comma 0 is in here. So the square root of 2 comma 0 is in here. This is the square root of 2, and also minus the square root of 2 is there. And then when y is when y is 0. So when x is 0, there are no points because minus 3y squared equals to 2. That has no real solution, so there's nothing here. So this graph is a hyperbola that looks like this. Okay, and what we're looking for is, are there points in here that have integer coordinates? Is there such a thing? And the answer is going to be no, and we're going to use congruences. So here's the solution. Suppose there is one. Okay, so one just like that. Then what this says is that n squared is 2 plus, let me write it actually as 3m squared plus 2. And you see, if I now look at the remainder of n squared when divided by 3, the remainder tells me here, let me use this color, the remainder, look at that number. That number is a multiple of 3 plus 2. So by the division, the division theorem, when I divide n squared by 3, there will be a q and an r between 0 and 2 included, that such that n squared is 3q plus 2. But I have it right here. So what this tells me is that the remainder, when I divide n squared by 3, sorry, is 2. So, okay, so the remainder is 2. But what happens when I square a number? What kind of remainders do I get modulo 3 when I divide by 3? So let's see. By the division theorem, also, we also have that the remainder when I divide n by 3 will be 0, 1, or 2. So every number n is either of the form 3 times k, or is of the form 3k plus 1, or it is of the form 3k plus 2. Okay, that corresponds to the remainder is 0, the remainder is 1, or remainder is 2 for some k integer. Okay, for some integer k. So let's see what happens when I square those numbers. What remainders do I get? So again, our assumption right now is that there is a solution to this equation with integers n and m and m. And we are going to see what happens if n is a multiple of 3, then n squared is, well, 3k squared, and that is 9k squared, and that is 3 times 3k squared. So the remainder when dividing by 3 is 0. Okay, that's what I indicate there with r. That's my remainder when I divide by 3. So n squared is going to be some 3q plus r. And on one hand, I have that the remainder has to be 2 if this was true. But if n is a multiple of 3, then I get that the remainder of n squared would be 0. So that is impossible and cannot be of the form 3k. Okay, so if n is of the form 3k plus 1, then what happens when I square it? I get 3k plus 1 squared, and that is 9k squared plus 6k plus 1, if I've done it correctly. And this is 3 times 3k squared plus 2k plus 1. So you see that now n squared is a multiple of 3 plus 1. So the remainder of dividing by 3 would be 0, would be 1, right? So which is not 2, like we had claimed here. So that is not possible. So we must have maybe that the last possibility, which is what happens when n is 3k plus 2. If n is 3k plus 2, then n squared is 3k plus 2 squared, and that is 9k squared plus 6 times 2, 12k plus 4, and that is 9k squared plus 12k plus 3 plus 1, and I can take a common factor of 3 here, and I get 3k squared plus 4k plus 1 plus 1, and then again I see that this number n squared would be a multiple of 3 plus 1, so the remainder when dividing by 3 would be 1, which is again not 2, and therefore we've reached a contradiction. Thus, the remainder n squared, if I write that as 3q plus r, r is 0 or 1, but never 2. Hence, n squared being of the form 3 times an integer plus 2 is impossible. Okay, so there you have it. So now we have a proof that there cannot be integer solutions in this hyperbola. Thus, the hyperbola, this hyperbola has no integral points. Okay. We are going to do this again once we have the machinery of congruences. We're going to be able to do this a lot quicker and a lot more briefly. So we'll get there. The last thing I want to talk about as an example, and I'm not going to do this, is that in applications, for example, in encryption, cryptography, these kind of things come up a lot. So what is, here's the question. So is the number n, which is 4 to the power of 3001 minus 1, is this divisible by 5? Is the number divisible by 5? Is it a multiple of 5? Well, this is a gigantic number, so a priori, it's not easy to tell. You can do some tricks and actually find out what the answer to that is. But again, this is a job for congruences. So congruences are going to help us answer these questions, or we'll come back to this question later and solve it in a very easy way. So let me go to define precisely what are congruences. So here's the definition. By the way, congruences was invented by Gauss, the actual definition I'm going to put on the screen now. And it was a revolution in number theory. Of course, before Gauss, mathematicians, Greek mathematicians were using remainders. But once you have this very powerful terminology and very powerful notation, you can get a lot farther than people had done before. So here's the definition of congruence. So let m be a fixed integer bigger than 1. Then we say that two integers, a and b integers, are congruent modulo m, and write that a is congruent to b modulo m if m is a divisor or divides a minus b. It's a divisor of a minus b. Or in other words, a minus b is a multiple of m. Also, if we fix an integer a and the modulus m, the set of all integers congruent to a modulo m is called the congruence class of a mod m. Okay, so this is what we define congruences to be. And then there is a congruence class of a modulo m, are all the integers that are congruent to a modulo m. So let's start by doing some examples. Again, let me write here that we say a and b are congruent if and only if m divides a minus b. So here's an example. So for example, the congruence a is congruent to 3 modulo 5. This holds because 5 is a divisor of a minus 3, which is exactly 5. So 8 and 3 are congruent modulo 5. We also have that 23 is congruent to 3 modulo 5, also because 23 minus 3 is 20, which is 5 times 4. So it's a multiple of 5. So 23 and 3 are congruent. What about minus 3? Is minus 3 congruent to 18 modulo 7? The congruences are good for any integer. So we also do congruences between negative and positive numbers. So this is true because minus 3 minus 18, that is minus 21. And minus 21 is a multiple of 7. It's 7 times minus 3. So yes, minus 3 and 18 are congruent. Okay, but 55 is not congruent to 31 modulo 7 because, well, 55 minus 31, that is 24. And 24 is not a multiple of 7. Okay. Let's think about also what the second part of that definition, which was a congruence class. So let's think, what is the congruence class of 3 mod 7? So 3 mod 7, let me write it like this. 3 mod 7 remember that it's really a set of numbers. So it's the set of all numbers, all the integers that are congruent to 3 modulo 7. So certainly 3 is there. And if I add 7, 10, that will be also a number in that set, because 10 minus 3 is 7, is divisible by 7, right? And if I add 7, I will get 17 and 24 and etc. Those all will be there. And in general, if I add 3, if I add to 3, let's say n is 3 plus any multiple of 7, these will be congruent to 3 modulo 7 because, well, 3 plus 7k minus 3 will be 7k. Is a multiple of 7, so it is, those two numbers will be congruent. So those are all multiples of 7. I can also subtract multiples of 7, and the same thing happens. 3 minus 7, that's minus 4, and then minus 7, that's minus 11, and minus 7, that's minus 18, etc. And then you see that, in fact, this is the set of all numbers that are 3 plus a multiple of 7. Okay, for k, any integer, I get exactly that class of numbers. All right. So now, how many different classes of numbers are there modulo 7? Let me prove a proposition here. So proposition, let m be fixed. Every integer is congruent modulo m to exactly one of the numbers in the set, what I'm going to call for now Cm, which is 0, 1, 2, up to n minus 1. In other words, for every n, there is some r in Cm such that n is congruent to r modulo m. So equivalently, by the way, what this says is, let me maybe write it as a remark here. So let's write it as a remark. What this is saying is that the integers are broken into these classes modulo m. So every integer is either 0 modulo m or 1 modulo m. Those are sets, so we should have a union of sets. So it's the class of 0 modulo m are all the numbers that are 0 modulo m, and then union the class of 1 modulo m, and union the class of 2 modulo m, and union up to the class of minus 1 mod m, right? Those are all sets. And you can see it, for example, we did it before. We had an example where we said that every integer was either 0 modulo 3, or it is 1 modulo 3, or it is 2 modulo 3, right? So that partitions the integers into exactly 3 sets. So the integers, there's exactly 3 bins, and that partitions the integers. And similarly, for any m, it partitions the integers in m bins. Okay, so let me prove that statement. So here's the proof. So we want to show that for every integer n, there is some r in Cm such that n is congruent to r modulo m, and in fact that it's unique, and r is unique in that set. Okay, so what is this r? This is exactly, so if we want to know what n is congruent to, what we're going to do is a remainder. So for example, let me start with an example here before we do that. Okay, before we continue the proof, let's see, what is r going to be? So for example, if I'm considering m to be 7, then C7 is 0, 1, 2, up to 6. And I want to know, suppose now n is, I don't know, 23. What is 23 is going to be congruent to one of those, and only one of those. Which one is it? Well, what I can do is just do long division by 7. 23 is 7 times 3, 21, plus 2, right? So what that tells me is that 23 is congruent to 2 modulo 7, because 23 minus 2 is 21, is 7 times 3, right? So what we've done to find that number is using long division. So now we can continue the proof. Oh, this was just an aside. So now in the proof, so by the division theorem, there are unique q and r integers such that n is m times q plus r, with they are unique if you make sure that the r is between 0 and m. But that means that r is between 0 and n minus 1. And the way constructed, we can see that n is congruent to r modulo m, because n minus r is mq plus r minus r, that is m times q. So m does divide n minus r. And since r is unique in this way, then it has to be the only one that works. Okay. Right, great. So so now we know how to find that that class in that remainder class. And so in fact, what we're going to say, now that we know that, so by this theorem, what it says is that for every integer, there is exactly one number in here that integer would be congruent to this number, and that we're going to give a name. We're going to call that the least non-negative integer. Okay, so let m and n, an integer, be fixed. The unique number r in CM, where CM was like before 0, 1, 2, up to m minus 1, such that n is congruent to r modulo m. That is called the unique number r, such that this happens, is called the least non-negative residue of n modulo m. Okay. And then we say that R is the reduction of n modulo m. Okay, so here we're defined what it means for the least non-negative residue and what is the reduction of a number modulo m. So, and as a corollary from what we've just seen, is that actually to find the least non-negative residue of a number, you just do long division. So, so what we've seen is that in the proof, and let n be an integer, then the least non-negative residue of n modulo m is equal to the remainder of long division of n by m, i.e. If n is m q plus r with r between 0 and m, then n is congruent to r modulo m, and the least non-negative residue is r. Okay, I'm not going to prove this. This was in the proof of what we just did and the proof of the proposition that we did a moment ago. Okay, so for example, when we were looking at the example of the clock, what we did was it was the 14th hour, and we said 320 hours go by. Then what's the time? Then what's going on here is that m is 24. We care about hours just modulo 24. And what we have is cm, in this case, is the set of hours in the clock in one day that we care about. And we want to reduce every number modulo 24. So when we had 14 plus 320, that was 334. Then what we wanted to do was reduce 334 modulo 24 to see what hour of the day that was. And what we found out in our example is that 334 is congruent to 22 modulo 24. And we did that using long division. We said 334 is 13 times 24 plus 22. And therefore 22 is the remainder of long division by 24. And thus it will be the 22nd hour, 22 hours, or 10 p.m. Okay. All right. The last thing I want to talk about is that, so here we are saying, for example, we had before that all the residue classes, when m is 7, every number falls under one of these residue classes. Right, this is what we're calling C7. But sometimes we want to change the residue classes to be other types of residue classes. So you might have other types of sets such that every number is congruent to a number in that set. So for example, let's see. For example, when m is 5, just for an easier example, C5 is 0, 1, 2, 3, and 4. Okay, and those are the sets of all, that's the set of all the possible least non-negative residues. But we also have that if you consider instead 0, 2, 4, 6, and 8, those are not non-negative, those are not the least non-negative residues, but every number is congruent to one of these modulo 5. So the way we would check is, does this set contain all the numbers, a representative of every class modulo 5? This is 0. Well, this is congruent to 0. This is congruent to 2. This is congruent to 4. So I have these classes are represented. And 6 is congruent to 1 modulo 5, and 8 is congruent to 3. So you see now I have 0, 1, 2, 3, and 4. So this set also contains one class of every congruent. They are not the least non-negative residues, but now it's a set that every number is congruent to one of these, but these are all even numbers, and for sometimes that is that's important. We'll see that, for example, when we do the proof of Fermat's little theorem. So every integer is congruent to one of these. Congruent modulo 5 to one of these. And such sets, we call them complete sets or complete residue systems. So let me define that. Complete, let again the modulus be fixed. Complete residue system modulo M is a set S of integers S1, S2 through Sm with exactly m integers Si for 1 from I1 up to m, such that each integer n is congruent to exactly one element in S. Okay, so what this says is that for every S, i.e. For every n, there is some S in S such that n is congruent to S modulo m. So for example, what I just did is that, 0, 1, 2, 3, and 4 is a complete residue system, modulo 5, that we know because those are the least non-negative residues. But we also have that 0, 2, 4, 6, and 8 is also a complete residue system. And again, what you have to check is that it has all the possibilities modulo 5. And that is because we have 0, 2, 4, 6, which represents 1, and 8, which represents 3. So they're all in there. Okay. We can also do a residue system with just odd numbers. Let's try that. 1, 3, 5, 7, and 9. Is this a complete residue system? Well, let's see. We have 1, 3, 5 is the class of 0, 7 is the class of 2, and 9 is the class of 4. So I have 1, 2, 3, 4, and 0. So yes, I have all of them. So it is also a complete residue system. Okay. So I think for now, I think that's all I'm going to do in this video. And then next, we're going to prove some properties of congruences, which will be very useful to start doing some applications such as divisibility tests. Okay, well, so we'll stop here.